Okay, so let's get started again here. So today we will continue with logistic regression. We will talk, well, I don't have anything planned about project number 3 to talk about, but if you have any questions, I'd be willing to answer them. So in terms of where we are with Save Our Stats, of course, you probably heard the Faculty Senate on Tuesday voted no confidence on the Chancellor. This is the first time it's ever been done in the history of the university, and it was an overwhelming no confidence. This next goes to the Board of Regents, and hopefully they do the right thing. I don't know. So what can you do? Well, we're going to start a letter writing campaign number 2. We've talked about in the past about writing the academic planning committee. You can send a letter to the Board of Regents. I have some details about who to send it to, some ideas of what to talk about. I posted it to my various social media places. You can reach all of them by going to chrismiller.com on the left-hand side. If you by chance have never, or I'm sorry, right-hand side, if you've never seen it, just click on, 3 of these. So if you go to LinkedIn, eventually you'll get to there. You'll see the details of what you can do and have an effect. Of course, also, December 5th is the Board of Regents meeting. Anybody can testify or speak in front of the board. You just have to give at least 24 hours notice beforehand if you're going to do that. The person that you let know is what's called the corporation secretary. You go to the Board of Regents webpage, you'll see her listed there. Her name is Katie. You can email her and say, hey, I want to speak, and she'll put you on the schedule. This is how 3 of our faculty members testified during the last Board of Regents meeting. Note that there is a Board of Regents meeting actually tomorrow, which was unexpected. It has nothing to do, unfortunately, with the budget situation. It's just the fact that the University of Nebraska-Lincoln is essentially going to be, I'm going to say essentially, it's not exactly the same as it's going to happen. It's essentially being merged with University of Nebraska Medical Center. And the reason why that's occurring is because the medical center has tons of research dollars for all the medical research that they have. And if you put that with our research money, it makes us look better to the AAU to get us back into that elite organization. And so the board is going to likely approve that tomorrow. But since it is an open meeting, anybody can speak also at that particular meeting, but you needed to let the board know by noon today if you were going to do that. Unfortunately, most people didn't know that that was going to happen, and so they're probably not going to have as many people as they would have had if they had actually publicized it. Okay, so again, project number 3 is due on Wednesday, November 26th at noon. Please note that I might be slow acknowledging receipt of the project because I will be at a conference. And so again, November 25th, I will be at this conference, and after today's class, I'll make a judgment of exactly how we will still have class. Any questions? Yeah.
Will it still be recorded regardless of your decision for Tuesday's class?
Yeah. Any other questions? Okay. So we were talking about last time the sensitivity and the specificity relative to making predictions or classifications. And the sensitivity, simply defined as the probability you classify or predict something's to be positive, given it's actually a positive. Now, obviously, you might not necessarily have positive or negative as the possible options out there. We've been using also, like with the place kicking data set success, you kind of equate positive to the success of a place kick. So in that context, that's what the sensitivity will be for when we actually very shortly apply it to the place kicking data set. That's the sensitivity. The specificity looks like this. Oops, wrong one. It's the probability you classify or predict something as negative, given that it was actually negative. So just the kind of the opposite in terms of success, but still a conditional probability. And so relative to the place kicking data set, this would be, let's say, the probability we classify something as a failure for a place kick, given it was actually a failure. We want a sensitivity, we want a specificity to be as close to 1 as possible. The closer it is, the more accurate your statistical method is in prediction. So that's where we left off. Now let's go to the place kicking data set here. So a success for us was a good equal 1. Good was the response variable. Good equals 0 is a failure. And if you remember from last time, in order to use a logistic regression model to classify or predict for a particular observation, we have to calculate the estimated probability of success for that particular situation. And R automatically does that for us through a few different ways. So last time we looked at how to use the GLM function to estimate the model. Suppose we put those results into an object called mod.fit, for the lack of a better name, model fit. And one component of the list that's returned is called fitted.values. We saw something similar to this way back earlier in the semester with respect to estimating a regular old regression model. And so for observation number 1, pi hat is 0.943. For observation 2, it's 0.957, and so on. Now, a more general way to get these estimates of the probability of success here, pi hat, excuse me, is to use the predict function. Again, this is exactly what you can use with the LM function as well to get what we would normally call y hats. And so if I say predict object equal mod.fit, and I add just a little bit of code here in red, it still works without it because it ends up being the default. But I like to emphasize it. New data equal, let's say my data set that I'm working with, place kick. Say type equal response, because our response is y, but what we're really interested in is the probability y is equal to 1, or in our case, the probability good is equal to 1. We put the results into pi.hat, and then again, you get exactly the same thing. We can do a similar thing with the validation data set, but notice the one difference. And this is why I like to put new data equal place kick there. So we have this extra validation data set, and we can say new data equal valid, and we also get the estimated pi's. So using these pi hats, we can use what's called a cutoff probability to say this is going to be a success, this is going to be a failure. And suppose we use a 0.5 cutoff. So for this first observation here, is it going to be a success or failure? It's going to be success. Okay, very simple. So how can we get R to automatically do this? There's a few different ways. There's actually a more efficient way than this, but I like this because it relates it to something that you're probably all familiar with respect to, let's say, using a spreadsheet package. Okay, in a spreadsheet package, you often see a function called if. Well, R has something very similar to it called if else. So if I create an object called cutoff, give it 0.5, then say if else, I'm going to test a particular condition. Is pi.hat, remember this is going to be a vector of all our pi hats, so it's going to be like 1,400 some values. Are each of them greater than cutoff? So it goes to observation 1, it makes a check. Goes to observation 2, makes a check, and so on. And if the answer is yes, let's return a value of 1. If it's a no, let's return a value of 0. I'm going to put then an object called pred.good for predicting good. I do a very similar thing with the validation data set as well. So now that I have all these predictions, I have a bunch of ones and zeros. Now I can go back to my function that we've seen before, summarize.class, and have that summarize our correct classifications and our incorrect classifications. So I say summarize.class, my original, what was actually observed, that good variable, which happens to be the 9th column of place kick. I guess I could just say place kick $sign good. I didn't, but that's what I did here. And then say classify, well, our model's results were put in pred.good. Sorry. I think since the end of September, basically I've had some kind of cold or something. I'll blame the budget cuts. So basically what we just did here was resubstitution. Okay, because we're using the model to predict the observations for which the model was built upon. Of course, we know that that might be a little bit biased. And so this is what we get. Let's focus on the prop table or proportion table. So we can see that almost 99% of the observed successes were classified as success. Wow, that's great. But, and also I should say, this is the sensitivity. So it's the estimated probability, classify good as a 1, given the true, I guess I use the word actual good is equal to 1. It's a conditional probability. That wasn't written very well. If that's not clear, if you need me to rewrite it, I will. So that's the sensitivity. So we have high sensitivity. But look at this. This is the specificity. 11%. That's not good. So this 0.8896 is our false positive rate. We didn't review that, but that's something we talked about last time. This is our false negative rate. Okay. Let's look what happens now with the validation data set. Sensitivity is high. Specificity is really low. We can also look at the overall correct classification rate, 0.89 for resubstitution, 0.85 for the validation. So the overall rate is good. The question, though, is do you really want to sacrifice all those, our ability to predict the missed field goals? Yeah, that's a question for a football coach. So let's look at now a different cutoff probability. So I'm going to use exactly the same code that I had before, except for when I created the cutoff object, I'm going to put 0.7 in there instead of 0.5. Let's see what happens. My sensitivity drops a little bit. It goes to 0.91. This is with resubstitution. But look at my specificity. It shoots up to almost 0.5. Now, something that we talked about last time too is the relationship between sensitivity and specificity. There are ways to increase your specificity. In this case, what we did was you can say we raised the bar to have something declared as a success or predicted to be a success for a place kick. We raised the bar. And what did that do? It increased our specificity. Because it took more for us to say, yes, indeed, that place kick will be a success. And since it takes more, that means we will say we're going to predict more failures. But when we raised our specificity, look what happened. The sensitivity then went down. So maybe think of it from another perspective. Let's say that I changed my cutoff probability to be 0.3. What do you think is going to happen to the sensitivity? It's going to increase because it's a smaller bar to get over. I'm using the word bar relative to place kicks because you're kicking over a crossbar. Sometimes I amuse myself, and I'm sorry, maybe that wasn't funny, but I never realized I was doing that until just now. So we're lowering the bar. You can say we're lowering the crossbar for the field goal post or whatever. So we're lowering the bar to say something's a success. So that means that we will have more successes, but you're going to sacrifice being able to predict the failures. Our overall correct classification rate goes down a little bit. Why does it go down even if I'm increasing the specificity by so much? It's because we have so many place kicks that were originally a success. That's why. We have a very imbalanced data set. With our validation data, we have a similar thing happen. Sensitivity goes down. Specificity is now 0.6. They might be wondering, why is it so much higher there? This validation data set is much smaller than the original data set itself. And it just so happened, because of the particular observations that were in there, there's going to be, we end up having a higher rate of failures predicted correctly. And it's just the variability that you would expect when you have less observations. It could have went the other direction too. We're just going to have more variability to worry about. Okay. So that's resubstitution. And that is also if I worked with a validation data set. Now, another way to estimate the accuracy is to use cross-validation. Well, how can we do it? Well, we can write a function to do it ourselves. It's not that difficult. This is just a good example of showing what you can do yourself without necessarily searching all through our, maybe do a Google search and get away with it too. But searching all through R and trying to figure out what function is going to allow me to do cross-validation here. It's not that difficult to do yourself. So I'm going to create a function called CD for cross-validation. I'm going to pass in 2 bits of information. My model that I'm trying to estimate and also the name of the data set. So the first thing that I do in the function is I find how many observations do I have. So I look at the number of rows of the data set. Then I'm going to create a vector called pi.hat.cv. This is where I'm going to put all my pi hats that I get from cross-validation. It's going to allow me to save these results. And what I'm going to do is basically create a vector that has a length of n. So I'm going to need 1 pi hat for every single observation. Then we get into the whole cross-validation part. I use a for loop for r in 1 to n. I don't know why I use r. I probably should have used r there, but I did. I estimate the model just like what we did before, but look at this right here. I am removing that rth observation when I estimate the model, because that's what cross-validation does. It removes, at least the way that we've talked about it, it removes one observation at a time, estimates the model, does the prediction. So how do we do the prediction? We use the predict function like what we've seen. I put the results for this one observation. Notice how I put the one observation there for new data. I put the results of that one observation into pi.hat.cv, the rth element of it. And then I return, after that for loop, all the pi hats. Now, if you need to, step through this function yourself. Here's examples of what model would be. Here's an example of what the data set would be. And you could step through it by saying, okay, suppose R gets the value of 1. What's going to happen? Suppose R has a value of 2. What's going to happen? And just step through it to see the whole process, if you need to. So to run then the function, I say, okay, CV, I put my model, I put my data set, and I save the results into save.cv. Save.cv will have all my pi hats from using cross-validation. Once I have that, I can use essentially the same exact code as I was using before to get the predictions. So I set my cutoff, I use my if-else function, and then I use summarize.class. This is what we get. Notice the cutoff is 0.5 here. My sensitivity is 0.99, and here's my specificity of 0.1. The results are very similar to what we have with resubstitution. Why? Because we have a large data set. That one observation I'm removing from about 1,400 observations is going to have very little effect, typically. So that's why I get very similar results. So we can also do some plots. So here's a principal component number 2 versus principal component number 1. Looks very similar to what we've had before. And I'm using resubstitution here since it was similar to cross-validation. The blacks, that should be BL. The blacks are the failures, the reds are successes. These are the predictions. And we can see what we had before with discriminant analysis, especially. That PC number 1 is really corresponding to the distance of the place kick. The larger PC number 1 is, the larger the distance. And so we can see that what the model is going to do is predict those longer place kicks as failures at times. I don't think, though, if you compare it to discriminant analysis, we don't have as much of a distinct separation as we did before with discriminant analysis. So that's one difference. You can play around with a 3D plot if you want to. You're going to see the same thing. Suppose I use 0.7 as a cutoff. Look at the difference between this plot and the previous plot for PC number 2 versus PC number 1. Now we have a lot more black dots or black circles. Why? It's because, again, we have a bigger threshold or bigger bar, higher bar to overcome in order to say something is going to be predicted as a success. So therefore we have more failures are predicted. Where are these failures predicted? They tend to be for the longer place kicks. And one could actually dive deeper into this if one wanted to by looking at, okay, why do I have maybe this shape of a structure there? Well, if you remember, we have a lot of variables that are binary. And when we were first looking at this data set with respect to principal component analysis, I showed you a number of different plots so that you could see how the binary nature of some of these variables affect what we see here. And one could use that to further better understand why do we see these patterns here. Okay, any questions? Okay, so a question will often come then when you're using logistic regression models for prediction like this. And that is, for a particular cutoff probability, what's going to be my sensitivity? What's going to be my specificity? And, you might want to look at then this relationship in a nice organized manner so that you can decide, okay, maybe I need at least an 80% sensitivity. What kind of specificity can I get? Maybe if I get a little bit higher sensitivity, what kind of specificity can I get? And that's often a question that will come up when one's trying to do these kinds of predictions. Especially you see this with respect to like a diagnostic test, like to be test for an infectious disease. And to help people make these decisions about what should essentially be the cutoff probability, people will use what are called receiver operating characteristic curves, or ROC curves. People never call it ROC curves, even though you might think that. People will actually pronounce it as ROC curves. And all that an ROC curve is this. You plot your sensitivity versus 1 minus the specificity, which is the false positive rate. Remember what the sensitivity is? It's a conditional probability of the probability you predict positive, given it's truly positive, where 1 minus the specificity would be the probability you predict positive, given it was actually a true negative or actual negative. So we always have that positive there on the first part of that conditional probability. You plot these two for, let's say, a cutoff probability of 0.1, a cutoff probability of 0.15, a cutoff probability of 0.2, and so on. So I guess early on in my career as a professor, I came across this nice paper that I haven't seen anything better than it. So even though it's 25 years old, I don't think there's anything better than this. A nice paper that gives an introduction to ROC curves and why they are important. I encourage you to read it. I'm not going to ask you a specific question about it, but this will help you understand how these curves work. This paper comes, and this paper is available on my website. This paper comes from the magazine Scientific American. Some of you may have heard of that magazine before. The purpose of the magazine is to talk about various science items, we'll call it that, for lack of a better word, science items, but at a level so that people who are not experts in the area can understand it. And so we're going to take a look at just a small portion of the paper to introduce what these curves are. This is on page 85 of the paper. Okay, so we're looking at the plot that's in the middle there. So remember, you're plotting the sensitivity. Oops, let's move that out of the way. And let me make this just a tad bit smaller. There we go. So y-axis is the sensitivity. On this particular paper, they call it the true positive probability. Sure, that's fine. On the x-axis is 1 minus the specificity, or what they call the false positive probability. And so obviously these two axes go from 0 to 1 because they're probabilities. They'll be estimated probabilities for us. And if you notice here, we have a line that's drawn at a 45-degree angle from the origin. This is a line called the line for chance accuracy. What does that mean? Well, suppose I had a false positive probability of 0.3 that corresponds to a true positive probability. I'm sorry, I should use the words that we're using. I would have a sensitivity of 0.3, a 1 minus specificity of 0.3 as well. So you're going to be equal across that line. So you're right in the middle there. Notice what that means relative to the problem. That is, given it's an actual positive or given it's an actual negative, you still have the same probability that you're going to declare something to be positive. That's not good. Because you would hope that if it was a true positive, or actual positive, sorry if I keep on using different terminology. If it was an actual positive, you would hope that the probability you're going to classify it as positive is going to be much, much, much higher than the probability you would classify it as negative. So this is why this is called a line of chance, a line for chance accuracy. Essentially, you're flipping a coin. Okay? Now, what we want is what I'm going to highlight in blue here. So we'll look at how to actually construct this curve in R, but this would be our ROC curve. And what that's going to tell you is, again, for a particular 1 minus specificity, what is the sensitivity? So if we look again at this 0.3 for 1 minus specificity, we project up and over, we see the sensitivity is 0.88. So obviously you are doing much better than you did with the line of chance accuracy. And this sensitivity and this 1 minus specificity, just to make sure this is clear, all is connected to a particular cutoff probability. So if you were, let's say, working on a particular project where this was of interest, and let's say, yeah, I really like that sensitivity. I'll give up this error rate, this 1 minus specificity. I can live with that. I really like this sensitivity. The next step that you would do is, okay, what is that cutoff probability then that was used to produce that particular point on that plot? But maybe you might say, okay, I'm not satisfied. I need to have at least 90% for my sensitivity. So, you might come over here and project down and say, okay, well, I'm going to have to live with about a 0.45 probability of making a false positive. Maybe for a particular application that would be okay. So that's how you interpret an ROC curve plot and also the purpose of it. A question that I have given on a test before is as follows. I will actually put this plot without any curves or lines on it on the test. And I'll say to students, show me what the best possible case would be for an ROC curve if you want to do well in your prediction. Well, how would you draw it? Well, let me ask you this. Let me ask you a different question. Suppose I do a line that looks like this for a curve. Is that better or worse than the one that I have in blue? Worse. Suppose I do this. Is this better or worse? Better. And so I could keep on going, although it's no longer a curve. That would be the best. Okay? That's the ultimate goal. Now, something else I hope you've been thinking about, and if you haven't, that's fine. But I think we can agree that what's highlighted in blue is better than that line for chance accuracy, right? Okay. One way to make an overall decision about why this particular line would be better than the red line would be to say, hey, what's the area underneath that curve? So I could find, obviously, this area. That area is 1/2. Half times base times height, yeah. Now, for the curve itself, again, I would find all that area. Let's actually even do this too. That area will be bigger than the area for the line of chance accuracy. And so as an overall way of saying, yes, that method is better, we could look at the area underneath the curve. People will always want to estimate that. And this also comes into play in the following situation. Oops. The main thing is notice how the lines cross. And you might need to make a decision between these two as an overall measure. And obviously you could look at particular sensitivities, particular specificities, but sometimes people will say, hey, let's just look at the whole area underneath the curve. Which one's bigger? The one that's bigger is a better method. Okay. Let me go back to my notes to make sure I talked about everything that I wanted to. Yeah, I did. Any questions? Okay, so let's apply this to the place-kicking data set. You'll see RLC curves used a lot in medical studies, because you're often talking about, well, did the person live or die, or were they cured of a disease or not? Tons and tons of binary applications in the medical sciences, and they want to have particular diagnostic tools or particular ways to make an understanding of did a treatment work or not. And they often use RLC curves for that purpose. But here we have something that's important maybe to other people as well, and that is we're talking about football. There are a number of different packages in R that produce these RLC curves. I've never been completely satisfied with any of them. What I'm going to present to you is just what I've judged to be the best, but it's not necessarily as straightforward as it should be to get this stuff done. The package I'm going to use is what is called RLC R, RLC curve R. And I apologize, I never even mentioned what RLC stands for. Receiver Operating Characteristic. And then a curve, ROC curve, where these curves originated from was actually during World War II, where one of the innovations that the United States and the UK had was that they developed radar technology. And as you can imagine, with a radar system, you want to know, well, is that a German airplane that's coming, or is that a bird? Or something like that. And they use ROC curves to help them make that judgment about how good their system was. And so that's how it originated. So you can think of receiver, they're receiving a signal and an operating characteristic. How good is this working? ROC curve. Okay, sorry I didn't say that at the very beginning. Now, the thing that makes this particular package a little bit more complicated to use is that it's what's called an S4 package. So when so understanding of the origin of R. So back in the 1970s, AT&T Bell Labs introduced a programming language called S. And S went through a number of different versions. Eventually, in the mid-1990s, some researchers at the University of Auckland in New Zealand decided to essentially make their own statistical software package based upon the same S syntax. So at that time, is often referred to as, it's not unlike S. Why did they do that? Because there was a software package that you had to actually purchase called S+. That was based upon the S language, and they wanted to make something that was freely available. So that's how R came about. And R was originally based upon a version of S called S3, S version 3. Still, even now today, almost everything in R is based upon S version 3. But as you can imagine, since the mid-1990s, there's been other versions of S that have come about. One of the first ones was called S4 in the early 2000s. It never really caught on very well. There's been other versions. People no longer use S version, whatever anymore. Now it's more like R version, something like that. And there's been other versions, but they've never really caught on as much as using S version 3. That's some background. The reason why I wanted to tell you that is because we're going to use something that's a S version 4 package that has a little bit different syntax of how to do stuff. Just out of curiosity, especially for the stat majors here, do you ever talk about the different versions of S and R or anything like that? Okay. Yeah. Thank you. Now, as you can imagine, why are people developing new versions? Well, there's can be little advantages, but there's never been such a huge advantage that people say, okay, let's abandon S version 3. Now, different underlying versions of S language or R language is a little bit different than, let's say, having a different dialect of the language. And that is essentially what RStudio, or POSIT, I forget how you pronounce it now, but the people who make RStudio, they have what's called the tidyverse. They've basically created a whole new dialect of R for their own for-profit reasons. And this is the only time ever, well, we'll say essentially the only time ever that a group of people that wanted to make a profit have been behind trying to make changes to how we use R. And so guess what? They're the only ones who've been successful. And the tidyverse is widely used by people. I don't like to use it for the reasons of from a for-profit company, although it is for the public good, that company. That's how they've incorporated themselves. So that is a good thing. But anyway, so they have their own version, their own dialect of R, which is different from what would normally be used in R. Anyway, I'm getting off track now. So there's a number of steps that we need to follow to get to the actual main, I'm going to ROC curve. So there's not like one function where I can say, hey, go produce this ROC curve for me. Instead, I have to go through a number of steps to get there. You could say that this is step 1. I use a function from this package, which you would need to download and install, called prediction. That makes sense to have a function like that because we want to get the pi hats for a particular cutoff probability. And so I say prediction, and then the first argument is called predictions. And I put my pi hats that I've created from the model. And then I have labels equal. This is where I put my good variable that has the true successes and failures. Now, why do I do that? Basically, what this function is going to do is look at a whole bunch of cutoff probabilities that it develops itself. And for each of them, calculate the number of, let's say, false positives that would result from using that cutoff probability, the number of false negatives, and so on. You can calculate areas underneath the curve, areas underneath the ROC curve as well. So it's going to do a whole bunch of different calculations, and it puts it into a list type object. I decided to call this list save.pred. Now, here's the first place where you're going to see a difference between S version 3 and S version 4. Normally, to see what's inside of a list, we just say names. Here instead we say slot names. Where does the name slot names come from? Well, with a regular old list, the actual parts of the list are called components in R's terminology. In S version 4, they're called slots. You know, it's kind of like some people will refer to the Chancellor's proposal, a distributed model versus a collective. It's just a rebranding. Anyway, so we have these slots. Here are the slots. Notice how this is kind of organized just like how you would normally see with if you use the names function. Now to access the slot, instead of using a $sign, we use the @ symbol. That's it. For people who are just wanting to use S version 4, that's pretty much all you need to know in terms of the differences. And so one particular slot is FP, which stands for false positives. And so to access components of let's say just in S version 3, to access components of a list, again, note that you would say $, whatever. There's another way that sometimes is not taught, and that is each list, and even though this is an S version 4 list, I can do this too. Each list has a particular number associated with, each component of a list has a particular number associated with it. And so instead of actually specifying the name of that component, you can actually specify the number. And so to do that, you could actually instead do a double set of brackets and the particular number. Now this is going to give you a little bit more of a complication here. Notice I say at FP, then I say bracket, bracket 1, and bracket, and bracket. Why? Because FP itself is a list. So it's like a list embedded inside of a list. And I just need the first component of it. And what this gives me is what was the false positive rate? I should have said that before. What is the false positive rate for whatever this function chose for the first cutoff probability? So in this case, the false positive rate was 0. And this is going to be a long vector. Yeah, I guess I can do that. I'm sorry, I did misspeak there. I apologize. It's what I had said before. Then I change. This gives you the number of false positives for a particular cutoff probability rather than the false positive rate. It's the number. So if I look at all this whole vector here, and obviously we get to a certain limit, so it doesn't show you everything. But for whatever the first cutoff probability that this function chose, the number of false positives was 0. For the second cutoff probability, it was also 0, and so on. And so as you can see, and this actually corresponds to the cutoff probability increasing, the false positives increase as well. And you can see with the tail function, those are the last few that we don't see here since it was stopped. Well, what are the corresponding cutoff probabilities? And I'm doing a poor job sometimes explaining this. I apologize. I'm making small errors in being precise in my language. So again, what we have here is the number of false positives. The corresponding cutoff probabilities is in cutoffs, that slot. And so, for example, when I have 163 false positives, the cutoff probability was 0.2375. Any questions about that? Yes?
Is there a specific way to picking these cutoff probabilities? Because I figured they would just be like kind of segmented, but they seem like random almost up there.
That's a good question. I believe the way that they're actually chosen here is that they're actually using the observed sorted pi hats. I am fairly confident that is the case. In the end, it's not a big deal, but I'm fairly confident that's how they come up with that. Okay, so then next. So a bunch of calculations are being done here to help us eventually get to that RLC curve. You can say now step 2. There is a function called performance in the ROCR package where notice save.pred goes into the first argument, prediction.obj object. And then I ask it to, okay, now I want you to calculate the stuff that I want to display on my ROC curve. Measure equals sense for sensitivity. X.measure is just a way to say what's going to be on the x-axis. I don't know why they don't have y.measure. They just have it measured. X.measure, FPR. And again, if you just look at the help for this function, you'll see what that means. False positive rate. 1 minus the specificity. And so what do you get out? Notice intuitively, you think, okay, I have some stuff corresponding to my x-axis and my y-axis. And indeed, that's what you do. So x.values gives you the corresponding sensitivity for a cutoff probability. Y.values gives you the corresponding 1 minus specificity for a particular cutoff probability. And R, or this function, puts the cutoff probabilities in alpha dot values. I'm not for sure why it uses the alpha word for it, but that's what it does. Then, finally, step 3, I can use the generic function plot with this object. So what's going to happen is plot is going to look at what's the class of save.perf. That's where I save the performance calculations. Then it's going to find a method function called plot dot. I don't remember what the actual class is. And it's going to do the plot. This is what it looks like. I usually like to put grid lines on a plot to help you see stuff, and especially in this particular case, it's very helpful. Normally, the way that you see me do it is to use the panel.first argument of plot. The panel.first argument does not work with the method function associated with this particular plot. So I add the grid lines in the end by just simply saying grid. And this is what I get. So here's our RLC curve. So if you wanted to, you could put the line of chance accuracy right through here. We can see that we're way above that, so that says that we are having some predictive power. So for example, if I want a sensitivity of 0.8, I would get a 1 minus specificity of about 0.23, 25 or so. And so what you could do is show the football coach, hey, here's my ROC curve. What do you think? What do you think we should do relative to make a decision about attempting to place kick or not? Of course, that football coach would think you're kind of weird to say, here's the ROC curve, but that's how decisions could be made. Okay, let's see here. So now you might want to have, let's say, the actual 1 minus specificity for a particular sensitivity for a particular cutoff probability. Or you might want to have a particular sensitivity for that particular cutoff probability or whatever. How can you go about finding it? It's not as easy as it should be, but this is how you would do it. So what I can do from after using that performance function, I can extract all those corresponding values that would be in my x-axis and put them in an object called 1.minus.spec. How do I do that? I go into the results from that performance function. I use the at part instead of a dollar sign since it's S4. And I say I want my x.values. And again, it happens to be returned as a list, even though it doesn't need to be, but it is. And so I say I want my first part of that list. I do a very similar thing with my sensitivity values, where I look at y.values now, that slot. And then also I can do a very similar thing with alpha dot values too to get all my cutoff probabilities. So to illustrate the process then of how one would go about doing this further, let's say that I'm interested in specifically having a cutoff probability about 0.5. What would be the corresponding sensitivities? What would be the corresponding 1 minus specificities? How could I see those? Well, we use some kind of tools that we've kind of done before, but also some stuff that's kind of new too. So in other words, I'm sorry, I misspoke there. Suppose I want to specify, suppose I want a 1 minus specificity of 0.5. What would be the corresponding sensitivities? And if we look at the plot, you can get a general idea, but you're not going to have the exact value. So I'm right here. If I project up, we can see that we should have approximately about 0.9 or so for the sensitivity. So what I'm going to do this here is create a vector of trues and falses that tell me, am I around 0.5? So I say 1.minus.spec greater than 0.495. So run that code. Notice I get a bunch of trues and falses, although we only see the falses. Also, I say 1.minus.spec less than 0.505. I'm going to get a bunch of trues and falses. Okay. And then I say, okay, I am interested in when they're both true. And trust me, they are both true at times, even though we didn't see it there. They are both true. So when they are both true, I want to put the results into something called CK for check. Okay. Now let me ask you this. Suppose I did sum of check. What are the sums of trues and falses? What's R going to do? Is it going to produce an error, or is it going to do some kind of calculation for me?
Well, out of all the trues, right? Because true is 1.
Yeah. So it's going to treat the trues as 1, falses as zeros, and indeed we did have some where I had true and true. Okay, well, we had 7 of those. So then what I can do is say, okay, let's go into all my sensitivities, and I only want to extract when I have a true. Same thing with the 1 minus specificities. Same thing for the cutoff probabilities. We put this all into a nice little data frame, and voila. Here, for a 1 minus specificity around 0.5, we can see what the corresponding sensitivity would be. And as we said, it would be probably about 0.9, and indeed it is. We can also see what the cutoff probability would be as well, about 0.7. So, a question I might ask you on the test, I might say this. Suppose instead for a sensitivity, we want a sensitivity of 0.9. Tell me what the corresponding 1 minus specificity would be and what the cutoff probability would be. How would you do it? You adapt this code. How do you check your answer? Well, you can do the plot and get a general idea of if you're right or not. Excuse me. There's other versions of this plot that you can do. You can add additional options to it. You can add colorize equal true. You can also add print.cutoffs.at. In other words, tell me what cutoff probabilities you want to actually display essentially on the plot with everything else. And so, you could create a sequence of numbers, and that's what I did here, a sequence from 0.3 to 0.9 by 0.1. And this is what we get. So what that colorize option does for you, here's the corresponding, the corresponding legend, you can see how that line is changing colors corresponding to that legend. Excuse me. And we can also see the corresponding cutoff probabilities. Remember how when we had about 0.9 here, just a few minutes ago, we had a specificity about 0.5. We said the cutoff probability was about 0.7. So you can see how useful that can be. What if we use the validation data? So I can take my pi hats that I had before from the validation data. I put in for labels, well, what were the actual good results? And then I just follow the same code as I did before. And here's my RLC curve for the validation data as well. Very similar. There's a lot of other kinds of plots that you can do too. I'll let you look through the details. We'll just focus on what they look like here. So, for example, I could plot the sensitivity versus the cutoff as well. And so each of these points then corresponds to a 1 minus specificity. And so why would you want that? Well, let's say I was really interested in 0.8 as my sensitivity. Well, now I can find out what that cutoff probability is quite quickly. Sorry, I'm just a little... So this next text then talks about what I was referring to before with the area underneath the ROC curve. And that's a way that you can compare two different, let's say maybe two different logistic regression models. In fact, we'll do that kind of next. Okay. So let's go back to this performance function. Now, I can use this performance function with save.pred again, which came about through the prediction function. And then for my measure, before we had sensitivity, I can actually put AUC for area underneath the curve. And it will calculate it for me. In this particular case, then, you only happen to have one value because it's one curve. And if you look at y.values, we see my area underneath the curve is 0.847. For the validation data set, it's 0.839. What's the largest value that you can have for area underneath the curve here? For, let's say, the best possible ROC curve? 1. So we can see we're getting there. We're getting close to 1. Now let's look at a situation where we have multiple curves to look at and make a decision about which is the best. So suppose we consider a model that has only distance in it, a model that has only a lap 30 in it. Lap 30 is how much time's left to go essentially in the half of a football game when the place kick is attempted. We'll also compare this to the model that had all the variables of interest in them too. And so what you can do is estimate the models just like what we did before. I'm not going to go through the details because it's just like what we did before, but just a different model. We can also do exactly the same as before to get the necessary things for the ROC curve. And so what I do here first is when I use plot, I'm going to use the save.perf that corresponds to this model that has all the variables in it. I'm going to plot that first. I'm also going to put in the corresponding cutoff probabilities on it too. But then next, for the model that has only distance in it, I'm going to add that to my plot. Notice I put add equal true. I'm also going to make it a different color than the default, color equal red. Then we do exactly the same thing for the model that has elap 30 only in it. Add it, color blue. I put a nice little legend on my plot to say which is what. And this is what I get. So what do you think about a lap 30? Do you think that's doing a good job? No, it's not. I would not want to use that model. I would not want to use just that variable alone. But take a look at the black and the red lines. So the black line has all the variables in it. It includes a lap 30, includes PAT, includes wind. Wind, for example, had a marginally significant value. PAT did have a significant value. If you look back at the hypothesis test, change had a marginally significant value as well. So we're getting some evidence. If you look at the hypothesis test, we were getting some evidence that indeed there are some variables in addition to distance that were important in predicting the probability of success. Compare the black to the red line here. Black is the full model, red is modeled with only distance. What do you think? Which is better for prediction? Essentially the same. The black is a little bit better. Just a little bit. Is it enough better to dump the model that has only distance in it? At least using my football background, I would say probably not. But one of the reasons why I bring this up is that make sure you understand the difference between statistical significance. That indeed, let's say that there is a relationship between, let's say, PAT and the probability of success. The difference between that statistical significance and what we are trying to do here, which is predict, is it a success or failure? There's a difference between the two. And so what we can see here is that what you might have thought intuitively coming into it, that, okay, well, we had all these other variables and some of them were important. I should be able to do a lot better. That's not necessarily the case when your goal is for prediction. Let's look at the area underneath the curves. So the model that has all the variables in it is 0.847. The model that just has distance in it is 0.838. So we can see they're close. We can see the model that has more variables is a little bit higher. But from a practical standpoint, it's difficult to say that that's enough to make a difference. Take a look at a lap 30, 0.56. Okay. Are there any questions? Okay, let me see here. I don't think I'm going to be able to finish this part next. Yeah. So I think this is a good place to stop. And then I'll make a judgment, hopefully this evening, about what exactly next Tuesday's class will look like. Let's now go back to this document. So what's next for our class? I'll have office hours. Tuesday's class format will be decided hopefully soon. Looking further ahead, project number 3 is due Wednesday, November 26th at noon. Again, it's extra credit. You don't have to do it. Now, the next time that we will have a regular meeting will be then Tuesday, December 2nd, because we have Thanksgiving. So we won't meet next Thursday. For that next class, what we will do is finish up logistic regression, and then we'll start a new section, multinomial regression, which is just the extension of logistic regression to more than 2 categories as the response, or more than 2 groups. A big thing that we will do, though, next time when we meet, like normal, is that we will review for the exam. So please be aware that that exam is coming up very soon here. Thursday, December 4th. Okay? Any questions? Okay, that's all for today.